Have you ever stopped to think about what's really going on when you move around on something that can also move, like, say, a small boat? We're about to jump into a classic physics problem that seems super simple at first glance. But trust me, the answer unpacks a fundamental law of how the universe works. Okay, so here's the puzzle. You've got a boy on a boat. He walks 3 meters from one end to the other. The question is, how far did he actually move forward relative to the water he's floating on? Now, your gut reaction is probably screaming, 3 meters, obviously. But not so fast. Physics has a little twist for us. You know, the secret to cracking this nut is to change how you look at it. Stop thinking of it as a boy and a boat. Instead, imagine they're a single item, a boy-boat system. The boy pushing off the boat's floor with his feet, that's an internal force. It's like two dance partners pushing off each other. Everything is happening inside our little system. Now, every system has this sort of magical balance point. It's called the center of mass. You can think of it as the average position of all the mass in the system. And here's the really cool part. This point does not care about any of the drama happening inside the system. The boy can do jumping jacks, the boat can rock and roll. None of that can move the system's shared center of mass. And this right here is the absolute key to the whole thing. The problem tells us to ignore outside forces like wind or water resistance. So since the boy's walking is an internal force, there is literally nothing pushing on our boy-boat system from the outside. And if there's no external push, the center of mass is completely stuck. It is locked in place. It cannot move. Period. Let's just think about that for a second. Before the boy started walking, the whole system was just sitting there, not moving. Its center of mass was stationary. And since we just established that no outside forces can act on it, that center of mass has to stay stationary. Its position just can't change. In the language of physics, the change in its position, what we call delta x cm, has to be 0. That one simple fact is going to solve everything for us. Okay, so let's look at the math for this. It looks a little intimidating, but I promise it's not. This formula is just a fancy way of finding a weighted average. You take the mass of the first thing times how far it moved, add it to the mass of the second thing times how far it moved, and then you just divide by the total mass. That's all it is. But here's where it gets really nice. Remember our big insight? That change in the center of mass, delta x sub cm, is a big fat 0. So we can just plug 0 into the left side of that equation. And when we do that, the whole denominator just disappears, and the formula gets way, way simpler. We're left with this beautiful little balance. The boy's mass times his movement has to perfectly cancel out the boat's mass times its movement. All right, time to plug in some actual numbers. Let's say the boy is 20 kilograms, and the boat is a heavier 80 kilograms. Now, here's the part that can trip people up, the distance. As the boy moves forward, he pushes the boat backward. Let's call that backward boat movement x. So is the boy's real movement 3 meters? Nope. It's the 3 meters he walked forward minus the x distance that the boat slipped backward underneath his feet. His real displacement is 3 minus x. So let's just assemble the puzzle. We take our simplified equation and plug everything in. We have 0 equals the boy's mass, 20, times his movement, which is 3 minus x, plus the boat's mass, 80, times its movement, which is negative x. And believe it or not, the physics is officially done. Everything from here on out is just a little bit of algebra. Okay, first step of algebra, let's get rid of those parentheses. 20 times 3 gives us 60, and 20 times negative x is, well, negative 20x. Then we just bring down the negative 80x from the boat side. Easy enough. Next, let's group our terms together. We have a minus 20x and a minus 80x, so that gives us minus 100x. Now, we can just pop that over to the other side of the equal sign to make it positive, and boom, 100x equals 60. We are so close. And for our first big reveal, we just divide 60 by 100, and we get x equals 0.6 meters. So what does that number mean? It means that as the boy walked his 3 meters forward on the boat itself had to slide 0.6 meters backward to keep that center of mass perfectly still. Okay, that's really cool, but we haven't answered the original question yet, have we? We know how far the boat moved, but we wanted to know how far the boy actually moved forward relative to the water. Well, remember how we set this up? We said the boy's real final displacement was the 3 meters he walked on the deck, minus that backward slip from the boat, which we now know is 0.6 meters.
Which brings us to our final and kind of surprising answer, 2.4 meters. He walks 3 meters, he feels like he walked 3 meters, but relative to the shore, he only made 2.4 meters of progress.
So let's just put it all side by side. Our intuition tells us the boy moves 3 meters and the boat just stays put. But what physics reveals is this beautiful balance dance. The boy moves forward 2.4 meters, while the much heavier boat moves backward just 0.6 meters. It all has to balance out perfectly to keep that center of mass right where it started. So if you're going to take just one thing away from this, let it be this idea. Forces inside a system can rearrange all the parts. The boy and boat can move relative to each other. But those internal forces are totally powerless to move the system's overall center of mass. For that, you absolutely need a push from the outside world. And that leaves us with a really fun question to chew on. If a system can't move its own center of mass, then how in the world does a rocket fly through the vacuum of space, where there's literally nothing to push against? Well, turns out it uses the exact same principle we just talked about. It's just a matter of what you define as your system. Something to think about.